let's continue with significant figures. So we have to first remember where significant figures come from. And so they depend on the precision of our measured values given in a problem. And this is usually reflected from our glassware or laboratory equipment. And so some things to note, right? Like in your videos, when you're watching a scale, right? You want to record every value that you're given on the scale, and every value, even that zero at the end, if you happen to get a zero on your scale, right? Every value would be significant. If I remember correctly, most of our scales go out to 3 decimal places. And other examples were from your homework, your ruler. Again, it depends on the precision. If you're looking at a normal centimeter ruler, right, let's just say we have our 5 centimeter right here. So 5, 6, and then usually there's little markings every 10th place. So we know we can measure the 10th digit accurately, and then we can estimate the hundredths with, again, a usual metric ruler here. So again, 5.xx. There's our uncertain digit at the end where you made an estimate. All right, so then what we want to kind of understand is how do we write these appropriate sig figs, and then how do we convert them? And so some other things to note is don't include your conversion factors when you're trying to figure out your least number of sig figs. They're always treated as exact values. And so those would be relationships such as there are 12 pieces in a dozen, or these conversion factors. So 1 inch is 2.54 centimeters. So don't include those. Other exceptions would be discrete values that you can count. And so what I mean by that is, especially if you take a look at the homework, and we'll look at that example, and it gives you this problem of 12.3 grams divided by 5. Now, I admit this problem is ambiguous because it doesn't really tell you what this 5 is. But I would assume that let's treat it like some sort of mass average, right? And so we would not include the 5 as part of our sig figs, right? So we would rather say that we have 3 sig figs from presumably a scale. And so what we can again imagine this scenario might be, it's let's say we have 5 pebbles and we wanted to get their average mass. And right, you can hold those 5 pebbles in your hand, you can count them, and right, know that you exactly have 5. So then we could get, this mass average here. And then let's do it real quick, just as an example. So now 12.3 divided by 5. And it just so happens that that also gives us 3 sig figs. That is appropriate. So 2.46 grams there. And so again, this is for things that we can discretely count. Like, again, you can count every individual pebble, every dog in the room. And this would be different, right, from like population averages, where let's say you were trying to get an average population of, how many birds you have in a certain square footage. So that would be a little different. All right, so once we kind of figure out these little bits, you'll mainly be interpreting, of course, results from a problem. And so let's just go through these significant figures rules here. And our first one here is all non-zero values are significant. That makes sense. So we have this number 536. And so this one has, of course, 3 sig figs. And then our next rule is what I usually refer to as our captive zero. So essentially a zero between two non-zero digits. And so of course, if it is trapped, it is also significant. So this number 6,703 has 4 sig figs. So now the next two rules here are what I call our showing magnitude. So this is now different. And so now we're kind of switching over to not significant. And this is both showing magnitude. And so our first one here, leading zeros. So this is placeholder zeros to the left of a non-zero digit are not significant. So in this case, 0.0043, it only has 2 significant figures. And so that is because, right, these 2 zeros in front are showing how small. For our trailing zeros, notice how now this is showing how big. So again, right, both magnitude. And so now it says zeros to the right after a non-zero digit are not significant. So in this case, 7,000 has only 1 sig fig. If we look at this next example, 32,040, this zero is captive, so it is significant, but then this last one here is showing magnitude. And then back to being significant. So now adding accuracy. So this is the difference. And now this is showing how accurate or accuracy. So now it says zeros to the right after a decimal point are significant. So now we have 50.0 and this has 3 sig figs. So now we're saying, right, we can measure that accurately to the 10th place. And then that would make this significant as well. Looking at this one, 0.0600. So of course, this first one is leading. It's showing how small. But then these 3 would be significant here. And these last 2, again, show accuracy. And again, how to read this. So you report to one more than what you have markings for on these rulers or scales. Rulers or like graduated cylinders. And then again, on a scale, every digit is considered significant. All right, go ahead and pause here and you can look at these examples and we'll go over them. So now looking at this, looking at number 1, how many sig figs we have. So this would be 2, since these 3 zeros here are showing how big. Number 2, we have 3 sig figs. So all 3 are significant. We have our captive 0 case. For 3, we have 3 sig figs. So that last 0 is showing accuracy. All these leading ones are again showing, I meant to switch pens, are showing how small. And so something that you can do to make it a little bit more clear is you can also rewrite this in scientific notation. And so to do this one properly, again, we want to reflect our 3 sig figs. So we have 1, 2, 3, 4, 5, 6. So 2.10, and I want to include that 0 to show it's significant, times 10 to the negative 6 for our number. And now we don't have to worry about putting all these zeros here to show how small. Instead, of course, we use our scientific notation to indicate how small. And then now we can clearly see we have 3 sig figs. Again, don't forget to include that 0 to show all significant digits. For this next one, number 4, 2 sig figs. And then this one was tricky. And this is ambiguous. Again, not the best way to write it, especially if you've seen it in a textbook. You might be confused whether that's a period or trying to show accuracy. And in this case, it is trying to show accuracy of 2 sig figs. But it would be better to rewrite this in scientific notation, and you can clearly show, okay, 2 sig figs, yes. Other caveats, let's say on number 4, you wanted to show that it was accurate to a different place. That's again where your scientific notation will be helpful, excuse me. And so instance, let's say, so again, we're working with 4,500,000. And let's just say we could actually record it accurately to this value, to the thousands. Again, we don't really know what number this is. And again, it depends on your scale or the problem or whatever you're trying to show. But again, let's say we're trying to show that we're accurate to the thousandths place. So we can write 4.500 and then times 10 to the 6. And then again, that indicates accuracy to the desired location. Let's look really quickly at how to do our multiplication and division, and then addition and subtraction with our significant figures. And so I like multiplication and division. They're the easiest to understand. And so for these, you always report to the least amount of sig figs. And so in this case, and this is a good reminder to give yourself enough numbers when you take initial measurements. So we have 3.56 centimeters multiplied by 4, except we have 1 sig fig here, 3 here. This is our limiting one. And so we can follow along, punch this into the calculator, 3.56 times 4. And so we get 14.24. But again, since we can only report it to 1 sig fig, so now we have to round down to 1 sig fig, which gives us 10. Same thing in this case. So we have 4 sig figs versus 2. So even though we get this, once we punch it into our calculator, we have to rewrite it like so, rounding to 2 significant figures. Same thing in this one, only 1 sig fig. So that limits our answer. Looking at this last one here, this is all to show that these are conversion factors. So conversion factor, conversion factor. So all this does not count. And so we're only dependent upon our 2 sig figs here. And so that's why it is rounded to 1.4 meters. For addition and subtraction, this is, I like to think of as elementary school math in some ways, right? You want to set it up in this fashion. And then you report to the smallest after the decimal, or the least, really. Maybe I'll change that to least so it makes more sense. And so what we mean by that, again, if we line it up in this way, so we're seeing we have 3 after the decimal place in our first one versus 2. So this is our limiting. So we can only report to 2 after. So even though we get this from our subtraction, we round to 2 after, so 0.68. Again, another reminder to give yourself enough digits for accuracy. So this one, we have no numbers after the decimal place. So 457 centimeters minus 0.68. And we can only round it again to the ones place. So now we have to round it to 456 there. Now this last bit here just kind of goes over scientific notation, showing you the different forms of this. And so I won't belabor it in this video. If you need help, I would just reach out to me individually